Um, okay, so I think it is recording. Okay, so just a couple other things for the upcoming couple of weeks. So Dieter, who's online right now, he's another section leader. Since we never seems to have enough time to like cover everything, Dieter has agreed to hold a special section on Wednesday, this upcoming Wednesday. This is highlighted July 23rd from 6 to 8 p.m. And then he's actually just going to demonstrate GitHub and Jupyter Notebook and then VS Code. Okay, and then next Friday, Alex is going to be back. We're going to work on Breakout and then this pop-up shop. So the pop-up shop is basically an exercise about looping through dictionaries. This exercise is not on the SIP IDE. And so if you go to the forum, I have a link where you can actually download the assignment um, well, from the Google Drive. And then the week after that, I'm going to talk about images. We'll see how that goes. I won't be able to do nearly as good of a job as Chris and Alex, but I'll try my best. So images is a new topic that's not on the SIP IDE for sure. So I actually put together a folder with the assignment and the starter code. And since I'm not able to get the CS106A video, what I did this year, I can't promise I'll be able to do it for every single lecture, but I'll try as time permits, is I basically took Meron's slides and then narrated over his slides and then created a video. And so if you go to that folder that's on the Google Drive and just download the entire folder, all of the assignments, slides, and the video that talks about image will be in that slides. Okay. And then I will do a similar folder for the 2D list. Okay. And then two other announcements, our very talented musical Emma Wong is going to be performing on Castro Street, Mountain View this Sunday. So for you guys who are in the Bay Area, please come support Emma this Sunday. And I'm definitely gonna try to stop by. Not that I'm a big draw, but in case you wanna like meet me, I'm happy to treat you to boba. Okay, and so come by between 1 to 3, and then hear like Emma's like sing and play the I don't know what this instrument is called. Emma like guitar, ukulele, whatever. Okay. Um, and then just one other thing, okay. I did post this onto the forum, but I don't know if I can like keep posting updates about this before like the SIP posse or the SIP policeman is gonna like make me remove it because it's technically maybe borderline solicitation. But I am so incredibly excited about this program. I got an email earlier this week. This is a program launched through MIT. I know, like, I don't have a lot of loyalty to the like cardinal Reds of Stanford, but whatever. Okay. I mean, we have to go where opportunities take us. And so this is a program launched through MIT. And it's an interdisciplinary program, and they take people at all stages of their life. You can be like an undergrad all the way to like mid-career or even in retirement. And they want like all sorts of people. You don't have to be doctors. You don't have to be researchers. They're looking for like designer, business people, marketing people, and they're trying to form these like intradisciplinary teams of people to try to like solve um, problems in healthcare. And the best part is, it's entirely like remote, and then it should be compatible with whatever else you've got going on with your life. I mean, they don't pay you, but you get to work with really, really, really like bright, smart people. And they've actually put together a webinar which happened yesterday, and then I was listening to it, and then it just like reminded me of like what a great place MIT is. And so if you're interested, okay, I put the link here, and then I will post the slides after Chris's lecture. And then I would really, really encourage you guys to check it out. I think the deadline is sometime in August. Okay. So that's it. I'm gonna hand it over to Chris. Thanks again, Chris, for telling us about NumPy.
Yeah, of course. Thanks for all the announcements. Yeah, I'm gonna just start off. I don't have slides today, but we're gonna be going through basically like a run-through demo the entire time. But I'll go through kind of like an overview of what we're gonna cover today first, just so you can kind of get a feel for what we're gonna learn, and then just jump right into it. So first, there's this resource, this data science resource called the Python Data Science Handbook that I believe Dieter or someone else found. I was looking through it. It's a really good resource. So I was actually going to base the lesson off of that. So I think we should start off by installing that, which is a pretty quick process, kind of just cloning a GitHub repo, which helps us practice what we learned in the last session that I taught 2 weeks ago. And then afterwards, I did run out of time last session to talk about Jupyter Notebook. So I'll do a quick walkthrough of what it is and like how to use it. Dieter is going to cover Jupyter Notebook a little more in depth next week, I believe. So this will just be like a high level kind of getting your feet wet in trying out Jupyter Notebook. And then for the majority of the session, we'll be talking about NumPy. And I selected a couple of specific chapters from the Data Science Handbook that we can run through just to learn how exactly to use NumPy. And then I'll try to leave a little bit of time at the end for questions. But yeah, that's the plan. So starting off, I want to have everyone install the Python Data Science Handbook. So let me share a screen, my terminal. If everyone could pull up their terminal. This is what it looks like for me. So for Mac and Linux users, it should just be the terminal app. So on Mac, you'll be doing command space and then typing in terminal. And then for Windows users, we have git bash installed from the last session. So if you could open that, and then this is how we'll install it. We'll do a git clone. So actually, I'm getting ahead of myself. Let me share this tab. So this is the link to the Data Science Handbook. I'll share this in the chat. So this is the repository that we're going to try to clone. It contains basically all of the information that is in the book. It's a series of Jupyter notebooks, each with like its own chapter of information covering different topics. So in order to clone it, we're going to click this green code button. Sorry, it's a weird dimension. So we're going to click this green code button and then click copy here. So this is going to copy the GitHub link. And then now we can go back to our terminal to clone it. So with that link copied, we can type git clone. Also, sorry, before you do that, I would suggest changing into a directory that you want to download this repository into. So right now I'm in the documents, but if you want, you can navigate to like downloads or anything using cd, which is the change directory command. So I can do downloads. If you want to see like um, what what exists in your current directory and what you can like navigate to, you can type ls and it should show a bunch of like whatever exists in that current directory. So most of you are probably starting off in the root directory, which is this little tilde, and then you can just change directories into documents or whatever folder you feel comfortable using. And then now we can type git clone and then paste that link. And it should download all that information. For me, I already did it, so it says it already exists. So that's why it shows this message. But for you, it should say something different. Yeah, I'm going to give everyone a couple minutes to get that set up. Vicky, if we could do another poll, maybe, for when people are ready, that would be great. I still haven't figured out how to set it up. Vicky, sorry. You're muted, but I was wondering if you could set up that
Yes,
poll.
I
Oh,
did.
you're
Okay.
to rush.
And so when you're done cloning, just hit yes. I couldn't get rid of choice two, and so just hit yes, and then Chris will know you're done.
Perfect. Thank you.
Sure. It only took a couple seconds to download that.
Yeah, it should be fairly quick.
Yeah.
So hopefully it's going smooth for most of y'all. All right, we'll see if we can reach maybe 20 people. For now, let's just clone it. And then I'll show you guys how to open it up afterwards. All right, it looks like we have 20 people voted yes.
Okay, so I'm gonna
So
end the poll.
yeah, thank you. I'll just get started on the next step. And then for those of you who are still working on it, feel free to drop questions in the chat and we'll help you work through that. But basically, from the last session, you hopefully will have had Jupyter Notebook installed. So we're going to open Jupyter Notebook using the Jupyter command. So type Jupyter Notebook here. It should launch a bunch of text, and then it should open a tab in your browser. So that's going to look like this. Share my screen. And then for those of you on Windows, I believe it was called like Anaconda Launcher or Navigator. So if you could find that application, open it up, and then look for the Jupyter Notebook application. It should do the exact same thing and launch this this view on your browser. Yeah. Sorry, am I sharing the this Jupyter Notebook screen? Are you guys able to see the Python Data Science Handbook? Okay, thank
Yes,
you.
we can see that.
I'm fairly new to Zoom, so not aware of how to see that. But yeah, so this should lead us to the Python Data Science Handbook directory, which is what we just cloned. So this is going to show all of the content from that GitHub repository from our local device. So I'm going to try to introduce everyone to what exactly Jupyter Notebook is first before we get into any of these. So I'll start by inviting you guys to click this new button, and then it should say Python 3 IPy so if you click on that, it should create a new notebook, and it should launch a new tab, and it should look like this.
Sorry, Chris. What do you click again?
Yeah. So I believe I'm sharing this tab. So if you click this new button at the top, right?
New. Oh, yeah. And then Python
Top
3 or
right,
terminal.
and then it should create a drop down, and then Python 3, and that should launch a new tab.
Got it.
Yeah, and everything that we're doing here should be we should be able to accomplish on Colab as well, if people feel like they would prefer to use that. So as soon as you hit new and then Python, it should launch a new tab that looks like this. This is essentially like a completely empty Jupyter notebook. So this is kind of what like a process in creating a notebook will always start off with, is we are like creating the new notebook, and then it starts on this blank slate. We can start off by renaming it. So let's call it like first Jupyter notebook. And then that should change the title up here. Yeah, and then basically what we see here is like this is called a cell, and within a Jupyter notebook is comprised of like a lot of cells. Right now we just have this first initial one, and in a cell you can write basically just like Python code, and each cell can run independently of each other.
Hey, Chris,
So if you want to run a cell,
sorry to interrupt. There's a
yeah,
couple people in the chat that says when they try to launch the Jupyter Notebook, instead of Python 3, they have this Conda env base. I think that should work, right?
that should work. Yeah.
Okay.
Sorry if it doesn't look exactly the same.
Yeah.
Yeah.
And so for the people that have a question that says the Python Conda env base, just select that.
Yeah. Thanks for bringing that up. And feel
Sorry.
free to continue to stop me if there are other
Yes,
questions.
yes.
I don't have the tab open, so I'm not always able to.
We've got like Dieter and then Emma fielding
Yeah.
questions, but if there's questions we can't answer, we might stop you.
Yeah. Perfect. That sounds great. Thanks again. So yeah, moving on. This is a cell, and what a cell does is we can write code in it. So you can write something like print hello world, which I'm sure you are all familiar with at this point. And in order to run it, we can click this play button at the top. It's if you hover it for long enough, it'll say run this cell in advance. So what happens when we run this cell? As expected, it will print hello world. So yeah, that's how you run a cell. And then if you want to add a new cell, there's this plus button that creates a new cell. So you can add like as many cells as you want, and you can run code in each of them. So
Sorry, which one is the wrong button?
the run button is the play. Um,
Oh,
sorry, it's a little small, but it's between like the clipboard and
okay.
the stop.
You could
Um,
also use that run button on top, right?
yeah, you can also do this, and it'll say like run select. You can click run selected cell. Sorry. A shortcut is actually Shift Enter. So if you Like if I wanted to, I can clear the output. Um, yeah, so if I clear the output, then I can run it again, and it should run that cell if you hit Shift Enter. Obviously, you can't see my keyboard, but I typed that and then it ran it and then moved on to the next cell. So yeah, that's what that looks like. Let's delete all of these extra cells that I created. So yeah, I'm gonna run through a bunch of different examples of writing code in Jupyter, and see how like this is kind of different from writing code in like an IDE, for example. So another thing we can do is we can assign variables just like we do typically in Python.
All
So we
right,
can
Chris.
assign like the,
Sorry to
yeah,
interrupt. Okay, so for
no worries.
me, when I like try to run that code, I get this thing says select kernel. And then if I were to select Python 3 and then it doesn't actually run. Do you know why?
Um, it doesn't run. So is there an error message that appears, or is it just is nothing happening?
Okay, so basically when you do the select kernel, am I supposed to pick no kernel or what? Or cancel?
Um, I think you can click, if you click Python 3, it should be all right. Let me
S-
see.
Right, and so it doesn't execute.
Um, I see. Does your Jupyter look like this? The kernel, I'm assuming, is in the top right, like this button up here.
Correct.
And then you selected the Python 3 kernel.
Yes, I selected. Well, I mean, now I select. Yeah, yeah.
Okay. And then does this status show, if you hover, there's like a circle next to it. Does it say
Yeah,
anything?
it says kernel status connecting.
Oh, connecting. Okay. I'm not sure. It might take a moment to connect. Um, let's give it like maybe a couple of minutes to
Okay,
see.
feel
Otherwise,
free to keep on talking. I mean,
I'm not entirely sure. If you want to follow along, just like I'll show you like what the output looks like. But
yeah.
yeah, I'm not 100% sure. Like each individual environment is probably going to be like slightly different. So I'm not exactly sure what's going on. Um, but
And
it
now it
looks like
says
you
it's
are wrong.
disconnected. Hmm.
Hmm. Keep an eye on it, and then if we have some idle time, I can try to
Okay.
work with you to debug it. Um, hopefully, like what we're going through now is like fairly straightforward. Although it would be nice to try it out yourself. Um, but yeah, I'll continue with the code. So what we were gonna do here is assign the variables x equal to 2 and then y equal to 3. Um, so when we run the cell, nothing happens because we're not really outputting anything. We're just making some assignment values. So assigning variables doesn't generate any output, so the cell doesn't output anything. Um, if we create a new cell and we add our two variables together and we run that, this will output the value 5 because we're summing them together. And basically what a cell does is it will essentially call print on the final value in the cell. So for example, if we did something like x plus y and then x minus y in the following line, this would only print the final line, which is x minus y. So we would get -1. So if we wanted to show both, we would have to put a print statement around the first line. And that would basically print. You can see that they're on like slightly different lines. So the 5 is what's printed, and then the -1 is like the final output of the cell. So these are kind of corresponding. Um, so yeah, Jupyter Notebook essentially will just display the last line. And then if you want to display both, and if you want to display something that's not on the last line, you have to wrap it in a print call. Yeah, so that's it on that. And now let's do some things that are a little more complicated. So let's start by saying my nums equals 1, 2, 3, 4, 5. So remember, assignment doesn't output anything. So if we want to see what the content of my nums is, we can just add a line here, and this will return the value. So now we can see that my nums is this list of 1, 2, 3, 4, 5. So what we can do is we can loop through this and print every single item. So let's say for n in my nums, print n plus 1. So this will loop through every item and print that value plus 1. So you can see that this is kind of the output that we expect, 2, 3, 4, 5, 6. And yeah, this is just to show that we can do like pretty, I guess, familiar Python logic in the code. It's kind of just like here we have this notebook that allows us to play with different like code writing and stuff. So if we have we can do assignments and we can like play with them. And when assignments occur, they are remembered throughout the notebook. So even though, like, for example, x equals 2 and y equals 3 is in a different cell from this x plus y, because the assignment has already occurred, this cell remembers that and is able to run it. So yeah, that's kind of just like a high-level overview of how you can use Jupyter Notebook. It's a good, I guess, way to combine like this idea of like, or merge like the idea of Python that you were learning, I imagine in the Code in Place actual curriculum, and then being able to use that for data science or any other sort of thing that Jupyter Notebook might be useful for. So lastly, I want to go over a couple more features of Jupyter that might be useful later on when you're working with it a little more. So one thing is if we have something that we're confused about. So for example, if we want to know a little more information about this my nums array, we can add a question mark, and when we run it, it will tell us what the type is, what the string form is, and other information about it. And there's also usually a doc string that's assigned to it. So this is telling us that this list is just a built-in mutable sequence. You can also ask about functions. So you're probably familiar with the length function. So if you type length and then question mark, running that will tell us that this is what the function signature looks like. This is what the function is supposed to do, and then what the type is. So type is a built-in function. Yeah, and then another thing that we can do is, so let's say let's import something. So this is going to be something we'll cover later, but let's say import pandas as PD. So a lot of you are probably going to see no module found. If that's the case, then you'll have to install it. Although if people are installing Jupyter through Anaconda, then you might already have it. So if you're not seeing this as an error, then that's good. Otherwise, you'll have to install it. So in order to install it, we'll have to go back to our terminal. So you share. So we'll go here, and then you can see that this is Jupyter Notebook is still running. This is essentially like a server. So what people on Mac can do is hit Command T, and that will create a new tab. And then now we have like another tab open. I believe for people on, oh, is my screen not shared? Are people able to see this? Okay, cool, sorry. So this should share, if you hit Command T, it should open a new tab. So it will look like this. And for Windows users, you might have to just open an entirely new Git bash window. So just follow the exact same steps to create that new window. And then what you can do is, if you are on Anaconda, you can type conda install pandas. And then when you hit enter, it will install that package. I'm using pip, I think. So I'll type pip install pandas. Yeah, so it should show this. Whatever package manager you're using should be able to work. Just say like, most likely it'll be conda, but if not, try pip or pip3. Give that a shot, and then it should install. So now when we go back to this Jupyter Notebook window, previously it was showing no module found, but now that we have it installed, it should not output anything, which means that it was imported successfully. So this star means that it's still running. So now that the number shows up, it's been done running. So yeah, now that we've imported this, I wanted to show you how we can use Jupyter to help us out a little bit in our coding. So if we're trying to access like a function within pandas that we're not super familiar with, and we can type like the first couple letters, and then if you hit tab, it should show like the options that we have that start with that letter. So it's kind of like an autocomplete. So generally, this is not relevant for the topics that we're covering today. We'll cover pandas in the next session, but this is kind of just like a sneak peek of it. We're generally going to just be using data frames. So we can hit enter on data frame, and that will allow us to autocomplete it. So if you're either lazy and you don't want to type the whole thing, or you just don't remember what it was called, you can use tab to pull up the autocomplete. Yeah, so you can also hit Shift tab after you open parentheses, and it will show you how exactly to use the function, basically like a doc string. And it will tell you like what the function signature is. So this is basically what what you can pass into a data frame function, and then it also tells you what to do. In this case, it's like pretty wordy and hard to understand, but hopefully it will make sense after the next session. But maybe a better example would be to say like sum, which is something I think you all are familiar with, which is basically just like you can call sum on an iterable, essentially just like a list, and it returns the sum of that iterable. So this is a handy thing to use if you're ever forgetting like how exactly to use a function, or what it's called. So to summarize, it's like if you want to use tab, you can also just do it like this. It will pull up an autocomplete, and then if you want to remember how it's used, you can hit Shift tab, and it should show you this information. So that way you don't have to like go on Google and search for how to use sum. So just keep everything in one place, basically. Yeah. So one last thing that might be useful is some tools to debug in Jupyter Notebook. So let's like create an error that you guys might have seen before, which is like divide by 0. So we have x equals 1 plus 1, which is 2, y equals 1 minus 1, which is 0. And then when we try to divide by 0, this will give us an error. So what we can do if we're struggling to figure out like where this error is coming from, we can say %debug, and that will pull up this this like UI, which essentially tells us like what the error was, and then also gives us an interpreter that we can use to figure out like what's causing the issue. So if we want to see like what is x assigned to, we can see that x is assigned to 2 because maybe we can't figure out that 1 plus 1 is 2. And then if we try to hit y, this will tell us what y was assigned to. which tells us straight that it's 0 instead of this expression 1 minus 1. So at that point, we can figure out that, oh, we're trying to do like x divided by y, and y is 0, so that we're getting this division by 0 error. Obviously, in this case, it feels a little obvious, but when you have a little more code and assignments are not exactly clear, this can be pretty useful to help you remember like what everything is being assigned to and why an error is happening. But yeah, that's kind of the overall taste of what Jupyter Notebook is. If anyone has any questions, feel free to ask. Otherwise, we can get started on NumPy soon. What may be wrong when we hit tab, but it doesn't show options? If you're hitting tab, I think you should start with like there's either nothing that starts with that, or you need like a couple more letters. So when I hit A and then tab, nothing shows up. Maybe I hit like S or some create a new cell. Suddenly stopped working for me too. Yeah, it might be like a kernel issue. My page is definitely lagging a bit, but usually it should work if you hit tab and let it autocomplete. If it's not working, maybe type a couple more letters and see if that will pop up. Other alternative ways to install Jupyter. Yeah, there's a few ways. The most straightforward is definitely using Anaconda, at least just for like the sake of uniformity across the class. But if you search on Google like how to install Jupyter, there's like a bunch of different ways that it will show you. But yeah, typically like I would recommend using Anaconda since it's just installing like one software. When would you code in Jupyter Notebook as opposed to VS Code or another IDE? That's a good question. So Jupyter Notebook is nice because it allows us to kind of combine like code and documentation and like results all into one file. So this is kind of useful if you want to like if you have specific code where like the results are relevant or you want to describe something, you can share it with other people. It's basically just like a document that has code and can run code within it. So that can be useful in data science where like results are like a big portion of like what you're doing in data science. In VS Code or IDE, like you're writing code, and the results are kind of less important than like the actual code that you're writing, and the code like can run kind of separately from like the notebook. But yeah, for data science, Jupyter Notebook is definitely like the more preferred version, just because of how easy it is to share your results and data. Yeah, I think for the sake of time, I'm going to move on. One last thing before I jump into NumPy is kind of to illustrate like how notebooks can be like passed around with documentation and results. Like we can already see that code exists in the notebook as well as like, the results. Like these are all stored when we close this tab and reopen it, it's going to still like persist there unless we deliberately like try to clear it. But we can also add like a different type of cell. So all the cells that we've been doing right now are code cells, but if you add like a markdown cell, then you can write like the heading. If people are familiar with like the markdown language, this is basically just a way to format text. So you can write like headings, like heading one, heading two, and so on. And they're like different levels of heading. You can also bold text, like basically add formatting to it so it looks nice and pretty. Um, yeah, so that's it for the Jupyter Notebook tutorial. So now we're going to look into NumPy. So let me share a different screen. Just share this window. So when I can close this tab, and it'll put me back into this Python Data Science Handbook. Um, so this is what we cloned from GitHub earlier. So we're going to go into the Notebooks V1 directory, and this is showing all of the chapters that exist. Each chapter is its own Python Jupyter Notebook. So what we're going to start with is actually not the first one, but we're going to jump into chapter 2, which is Introduction to NumPy. So if you click on that, it should open it in a new tab. So I guess we want to learn what NumPy is. So this is a lot of words. I'll try to condense it into something that's a little easier to consume. But basically, NumPy is something that we can use to work with arrays of data efficiently. So the reason this is useful is because a lot of things that are digital can be represented as like arrays. So like for example, images can be thought of as two-dimensional array of numbers. Sound clips, one-dimensional arrays. Basically, a lot of computer-related things are or like data-related things digitally are represented as arrays. So NumPy is like an efficient way to store arrays and interact with them in ways that we want. Basically, like manipulating them so that we can kind of convert them into something more interesting to us. So if anyone has like a background in statistics, it's pretty similar to just like a Python version of like statistics. There's a lot of overlap within data science and statistics since they're like pretty much the same thing.
Hey,
Um,
Chris, do you think you could just say a couple words about how arrays are different than lists in Python?
yeah. So I'll definitely get into that.
Okay.
And this data science handbook talks about it pretty well. So I think this particular paragraph is like an intro to it, and then the next chapter we'll talk about it more. But yeah, NumPy is like an efficient interface to store and operate on dense data buffers. Is just like large copious amounts of data stored into arrays. So there is some similarity to the built-in list type, which y'all are familiar with, but the main thing is that they're more efficient, and we can see why in the next chapter. Um, so we're gonna start off by doing a couple things, just like installing NumPy. So let me clear all the outputs of the cells. Here we can also see this is like a Jupyter notebook, and like all this text, this entire handbook is stored in Jupyter. So this is another reason why Jupyter is pretty useful because you can store all of this text and run code like within one spot. So
Do
that's
you
super
have
useful.
to open that within Jupyter Notebook, or can you open it in like say VS Code?
I'm not super sure if you can open it in VS Code. It's possible that VS Code will have like an extension for it. I don't know if it natively supports it. But like for example, if you just directly go to like the GitHub and open the notebook there, there is like a visual way you can look at it. That's pretty similar to this. It's just that you wouldn't be able to run the code, but you're able to see like everything else.
Yes, that's what it kind of looks like. Because my Jupyter Notebook is not working, and so I opened it in VS Code,
Yeah. Oh, perfect. Yeah.
but
Um,
but it doesn't look like it's able to run those cells. in VS Code.
Yeah, I'm not sure about how the like VS Code integration is with it, but there are like you can see like on GitHub as well. You can scroll through it. It looks essentially identical, and like for these chapters, all of the outputs are already like present, so you don't actually have to run it. It like shows you what would be there if you ran the cell. But it's fun to just like hit Shift Enter and like see the code run sometimes. But definitely not necessary. Um, but yeah, for the most part, we're just going to be covering these topics like in the Jupyter Notebook. I'll run them for you. You'll see what it looks like. But yeah, let's start off by installing NumPy. So if you want to try, uh, for those of you who can, if you want to try running this cell, it essentially will import NumPy and then output what the version number of NumPy is. So for me, that's 2.02. If a similar error to before shows up when I was trying to import pandas, then you're going to have to do a similar thing where you go back to your terminal and you type conda install NumPy or pip3 install NumPy, and then let that install and then try running the cell again, and it should work. So yeah, moving on, we can also import NumPy as like an alias. So this way, whenever we reference it, we don't have to type out the entire thing. We can just type NP. I don't know why, but this is like pretty standard abbreviation of NumPy within data science. So yeah, by convention, you'll find that most people import it as NP. But again, you're welcome to import it as whatever you want. This is not like a strict rule. Just make sure that it's like a unique alias so that there's no confusion about what is being referenced. Yeah, and then built-in documentation. This is something we covered. So if you want to see like the built-in documentation, you can run this. And then it'll show NP as a module, blah, blah, blah. And then this is like the whole documentation that comes with NumPy. Yeah, and then there's also this, which we didn't cover. I find this to be like slightly less useful, but if you want to see what that looks like, oops, it doesn't even work. Yeah, let's ignore that. It should show like all the contents. Basically, like something that you can do just with tab. So if you want to hit numpy.NA tab, which is also currently not working for me, then it should show like what functions you can reference and things like that. So yeah, that's kind of the first step is just to import NumPy, and this is like exactly what NumPy is. So at the bottom, you can click into the next chapter, which is understanding data types in Python. You can also just go back to this like list of files, and then just click on 2.01 directly. So this next chapter talks about like, I guess, the difference between lists in Python and arrays in NumPy. We can kind of skip over a lot of these since like it's going more in depth than we really need. But essentially what it's saying like at the beginning is that lists in Python are very like free form. So there's no restriction on what types lists can be. Like the size is like pretty flexible as well. So for example, I know there's something. Yeah, so in this cell, under Python, this is more than just a list. It says that we can assign like this L3, like list 3, to be a bunch of different values. So like true, the string 2, 3.0, and 4. So when we run this, this comprehension, it will spit out basically like what the type of each of these items are in this list 3 that we created. And you can see that each of the items are different types. So first one's a Boolean, second one's a string, third one's a float, and the last one's an integer. So Python lists are, again, like very free form, and they don't really have restrictions on like what you can do with them, which is nice in some cases. But when it comes to efficiency, that's not super nice. And this like really confusing diagram is just saying that like when you store these things in memory, it like all of these arrows are kind of jumbled up, and like Python is doing the like is figuring out where each item points to for you, but these pointers all go in like a bunch of different directions, and it's really messy and not efficient. So, oh yeah, and then on the left here we have like a comparison as a NumPy array, as everything is just stored in sequence in memory, which makes it a lot easier to work with. So there's definitely pros and cons to both of them, but when it comes to data science, NumPy arrays are definitely on top, just because of how efficient they are. So we're gonna skip to creating arrays from Python lists. Um,
Hey
so
Chris,
yeah,
you might have mentioned this, but I believe, Python, or NumPy arrays, it all has to be the same kind of data, correct?
yes,
Right.
uh,
That's that's actually a significant difference versus list. Because list you could have multiple different data types. You could have like integer numbers, lists within list, dictionaries within list. But I believe like arrays, all have to be homogeneous.
yes,
Um, and then the one thing I wasn't sure is like if you have like higher dimension arrays, like 2D, 3D arrays, whether the sort of length of each of those dimensions all have to kind of match up to one another.
yeah, they have to match.
Okay. So
Yeah,
so um those are kind of like significant differences between list and then
yeah, yeah.
arrays. Yeah.
So yeah, I mentioned earlier that like Python lists can contain kind of whatever you want.
Mhm.
But yeah, that's a good point out, is that NumPy arrays have to be all the same data type.
Yeah.
And we'll see how that works when we run through some of these code cells. So yeah, essentially we're familiar with Python lists, but we'll see here how like arrays are slightly different just by kind of running through some of these things. So we're gonna obviously start off by importing NumPy, since we need to use that. We need the NumPy module in order to use these arrays. So yeah, we'll just run through these cells one by one. First, we'll create like a NumPy array just from like a Python list. So inside here, we've created this Python list 14253, and then we wrap that in a call to numpy.array. If you want to see what that looks like, we can use our trick to hit Shift Tab, and it shows the doc string, and this just creates an array. So that's helpful. So when we run this cell, it will show us like this is the array that's been created. It looks pretty much identical to what we have here, but remember that this is being stored in like sequential memory, so it's like an efficient Python list. Um, so uh, yeah, moving on. NumPy is constrained to arrays that all contain the same type. So if they don't have the same type, then NumPy will try to convert them into the same type. So here we have like 3.14. So this is a float, and we want to convert, or we see that it doesn't exactly match with 4, 2, and 3, which are all considered integers in Python. But NumPy kind of has an idea that like, okay, at least they're all numbers, so we'll convert them all to float. So we can say like, yeah. So actually, you can actually see that this array is containing like all floating point types. So like this dot that gets added tells us that. But you can also just output like the data type of the NumPy array. Again, since it has to be uniform across the entire array, we can just directly access the data type, and they should all be float like float 64 types. So yeah, that's what happens when we run it. If we try to do something like that NumPy will struggle to upcast, we can do like hello here. So this this is a valid Python list, but when we try to convert it into a NumPy array, um, it converts, I guess it converts it all into strings. But strings are a little bit harder to work with. But I guess that's how a NumPy casts it. Yeah, and then it shows the data type here is whatever this is. But yeah, you can see how that generally works. So yeah. Next, if we want to explicitly set the data type, so here we can see that the data type was float 64, but if we wanted to use float 32, or I guess if these are all integers, then we can explicitly set it by adding that argument to the NumPy array. So you can set like data type is here, and then it will show us what data type is, which is the desired data type for the array. If not given, NumPy will try to use the default. So it will try to figure it out. So
Chris,
yeah, now we can see this
Chris,
decimal appears. Yeah.
what does that number 32 mean in float 32?
Yeah. So I think it's covered here. So basically, like it tells us it's a different type of integer.
Oh,
So all numbers essentially like to give you like a crash course in it, all numbers can be represented in like binary, right? And this is like telling us how many digits it takes to or like how many digits up to how many digits we're going to use to represent this number. So like for example, int 8, if we're only using 8 digits, then we can only represent like negative 128 to 127. And the reason it's like not 0 to like 256 is because if we want to represent negative numbers, like the first digit is essentially used as like a marker of like whether or not it's positive or negative.
mhm.
Um, so yeah, the number is essentially just like how many digits we're using, binary digits we're using to represent that number. And it just tells us like what the minimum and maximum value of that number can be. So if we want to represent something like super big, then we're probably like, oops, we're probably going to want to use like int64, for example. If we want to represent something that's like greater than like 2 billion. So that's what that value means.
Thanks.
Yeah. So going back to this, yeah, we can always specify like what data type we're going to use, and NumPy will try to cast it into that data type. And then, unlike Python lists, NumPy arrays can explicitly be multidimensional. So, kind of like matrices, if that is familiar to you guys. But it's essentially just like a list of multiple lists. The thing about multidimensional arrays is that each like list within the list has to be the same length, which is what you were talking about earlier, Vicky. So if we run this, like what this code does, I'm not sure if list comprehensions were covered in code in place, but what happens here
No,
is,
no. Um,
okay,
they were not covered yet, but hopefully we'll cover them
got it, got it.
down the
So this
line.
is kind of like a sneak peek to um, what might be covered later. But essentially what's happening here is similar to a for loop where we're looping through each individual item within this list. So 2, 4, and 6. For the first one, we'll do range of 2 to 2 plus 3, which is 5. So that'll give us like this list 2, 3, 4. And then for 4, we'll do the same thing from 4, 5, 6. And then for 6, we'll do another range from 6, 7 to 8. So this gives us like a two-dimensional array where uh, each item, it's like a list of 3 lists where each list contains 3 numbers. So you can see like there's 3 items in the overall list, and then within each list there's another 3 items. So this gives us a 3 by 3 matrix or multi-dimensional array. Yeah, and it says the inner lists are treated as rows of the resulting dimensional array. So yeah, like each individual list is a row. So this will become pretty handy later when we're dealing with like larger amounts of data. And we want like each dimension to represent like a certain value. So yeah, a couple other handy things within NumPy are these functions that kind of create NumPy arrays for us that like pretty much like standardized NumPy arrays that are commonly useful. So like zeros will give us a one-dimensional, or like depending on what we specify, it will give us like an array of zeros. So if you look at the doc string, the first thing that we pass in is the shape, which is essentially like the size of the array. So when we specify 10, that gives us a one-dimensional array of 10 zeros. But we can also specify multiple values. So if we specify 3, comma 5 as our shape, and this is ones, which I'm sure you can guess creates an array of ones instead of zeros. So if we specify like multiple dimensions within our shape, then it will create that many dimensions for our array. And then full gives us an array filled with the value that we specify. Again, pulling up the doc string, this is what it looks like. It's filled with fill value, which is the second argument to full. And then we have a range. This is similar to like, yeah, the built-in range function, where we have start is the first one, end is the second argument, and then step is the third argument. So this will kind of skip 2 for every value. And if we look at the doc string, that should say the same thing. Yeah, start, stop, and step. There's a lot of different like combinations of it, similarly to how range does it. But yeah, it essentially just gives us an NumPy array if we want like in an evenly spaced out series of numbers. Linspace creates an array of 5 values. So this is similar to range, but instead we're specifying like our bounds and then like how many values we want. So this would be like 0, 0.25, 0.5, 0.75, and 1. So we're giving 5 values between 0 and 1. And then random just gives us random values. By default, it's between 0 and 1. And then normal, this is just like a normal distribution, which is just like a, which will probably be more familiar to people who have studied statistics, but it's just kind of like random values between like -1 and 1, kind of. Yeah, and then we have random integers, identity matrix. This is just diagonal ones, and then empty is just yeah. This is less important, but it's just like an empty array. It shows ones, but this is whatever happens to already exist. So this can be any value really, but we'll eventually like usually when you use this, you probably are going to populate it with different values later on. Yeah. So yeah, and then going on to the standard data types. This is kind of something that we saw earlier. There's a bunch of different data types that are supported by NumPy arrays. And these are kind of all of them that exist. So mainly like Booleans, integers, unsigned integers, which is basically like positive numbers, positive whole numbers, floats, which is like decimals, and then complex numbers, which I guess are just like, yeah, complex numbers from math. Yeah, so that's it for the data types in Python. So now we can move on to the next chapter, which is the basics of NumPy arrays. I'm gonna, I guess, give everyone a quick water break, maybe like 2 minutes, and then we can get started on this. And then if anyone has any questions, feel free to drop those in chat.
Vicky had a comment earlier, and it sounded like she was saying, well, lists are so much more versatile than NumPy arrays, and that's true. We are fixed to a type, but I think the multiple dimensions we can have is a real advantage. Say if you capture, your camera captures a picture, it's 2000 pixels this way, 1500 that way, and it has RNG and B, and you say, how do I best store this in a compact form? Then NumPy is a good way to do it, because each pixel of the R is 1 byte, 8 bits long for the intensity. You do that 3 for all colors, and then you have the 2 dimensions for height and width. So once you have a data set, that it's kind of natural to define it, and you know what the type should be.
Yeah, perfect. Thank you. Yeah, so the main thing that comes from like NumPy arrays are its efficiency. So like with most of the coding that you've done, I guess, it probably doesn't make sense to use NumPy arrays. Like you don't fully need that efficiency. You want like the flexibility over efficiencies. So Python lists are useful in cases like that. But what this is going to lead into is kind of us dealing with like large amounts of data. And when we have so much data, we want to be able to like manipulate it efficiently. So NumPy arrays, like being able to store all that data efficiently allows us to like play with it a little better without, taking forever to run or crashing our computer or things like that. So I see there's also a question, what's the difference between lists and NumPy arrays with respect to the length of data? There's not much difference, I guess, in the sense that you can create lists of any length in Python and you can create arrays of any length. The only thing is like in Python lists, you can, I guess, freely add to like lists and increase the length of it. Whereas for NumPy arrays, you can technically increase the length of the array, but typically, like once you create an array, like its shape or like length is already set. So you're mostly just manipulating what already exists within the array. Arrays are not immutable, but generally, like we want to at least like I guess it does kind of sound like it's immutable because we don't really want to change like the length of it. But like you can definitely change the values of NumPy arrays, but like the size of it generally stays the same when we're working with it, just because like an array is considered something like the data that we're given. So once we initialize the array, like we're kind of just manipulating that. But you're free to kind of change it however you like. There's just like the slight nuance of like Python lists being infinitely, increasable, whereas NumPy arrays, like technically you can do the same thing, but generally you're not going to be doing that. But to answer your question in short, no, they're not immutable. Cool. Anyways, let's go on to the next chapter, which is the basic of NumPy arrays. This one is a pretty useful chapter, so we'll just start from the top and then go all the way through. So let's see, like data manipulation in Python, synonymous to NumPy array manipulation. We basically are going to see like how we can manipulate data and access them and like kind of play around with them. So here, I guess we'll see that it's these arrays are mutable. So yeah, basic categories of array manipulations, attributes of arrays. So like size, shape, data type, things that like data type we saw earlier, but we'll see like a couple other different attributes of arrays. Indexing of arrays. So this is pretty similar to indexing in Python lists. Same with slicing. There's a similar like format that NumPy allows. Reshaping arrays is kind of just like changing the shape of an array. So like shape is essentially like the dimensions size. So like we saw previously, like a shape could be 3, 5, which means it's three like values long in one dimension and then 5 values long in the other dimension. And then joining and splitting arrays, so combining and like splitting them up. So array attributes, first of all, we can have this. So you can ignore this random seed thing. It's basically just making our random spit out consistent values. So for this, we'll create 3 NumPy arrays, x1, x2, and x3. Should show nothing because we're doing 3 assignments. And then if we want to see what each of these arrays look like, we can create a new cell and kind of spit all of them out. So x1 is this, x2 is that, and x3 is this. So you can see that like the first one is a one-dimensional array, pretty straightforward, similar to a Python list. Second one is a two-dimensional array. So this is 3 by 4. So we have 3 rows and 4 columns. And then the last one is 3-dimensional, 3 rows, 4 columns, and 5 third dimension items. So yeah, this one looks a little less intuitive because 3 dimensions is to represent. But you can see that like each, it's like we have 3, you can think of it as like 3 two-dimensional arrays, and two-dimensional arrays are like, this would be like 3 two-dimensional arrays and then 4 one-dimensional arrays. But yeah, if that makes it more confusing, then you can ignore that statement. But kind of like take a look at the representation. So like you can see the dimension that has 5, we have 5 items going this way. The dimension that has 4, we have 4 items going vertically. And then the dimension that has 3, we have 3 overall items. So that's kind of how X3 is structured. So you can also print like a couple of attributes for arrays. So this one's printing like the attributes for x3, which is this big one. So you can see that like it has 3 dimensions. The shape is 3, 4, 5, and the size is just like the total number of items within the list, or the array, sorry. Here, let me also clear the outputs. So this should generate the same values because of a random seed. And then print out these things. Data type is int64. And then we have item size and n bytes. Item size tells us the size of each array item in bytes, which is essentially like similar to like, think of like digits, binary digits to represent a number. So this would be 8 bytes. And then the total, I guess, n bytes is the total size of the array. Yeah, n bytes is equal to item size times size. Yeah, so these are kind of like, if you want information about your NumPy arrays, you can access these attributes. So that can be useful later on. So we also have array indexing, which is pretty similar to Python lists. So looking at x1, we have this one-dimensional array. So if we want to access the 0th element, then this would give us 5. And then the fourth item would give us 0, 1, 2, 3, 4. Yeah, 7. And then you can also index from the end of the array. I believe you can do this in Python as well. So this gives us like the first one from the end and the second one from the end. So this gives us 9 and this gives us 7. It becomes a little more complicated when we have 2-dimensional arrays. So you'll have to specify like an index for each dimension in the array. So if we want to access this 3, then we would have to do 0, 0, since that gives us like the 0th row and the 0th column. And then 2, 0 will give us the second row in the 0th column, I believe. Yeah, so sorry, 0, 1, 2. And then 2, -1 will give us the second row, and then the first one from the end. So that should give us 7. Yeah, and then here we can see that these arrays are immutable. We can modify them using the same notation. So we can set like 0, 0 to 12 from 3, and that should change it to 12. Yeah, and then unlike Python lists, NumPy arrays have a fixed type, which we mentioned earlier. So if we try to mutate the NumPy array with a non-integer type, so here like we know that it's an integer, from both like when it shows here and when we did data type, it will truncate it. So it will convert it from 3.14159 to 3. So truncating just means like converting it from like whatever decimal it is to an integer by just like completely removing the decimal part. So yeah. Then we have array slicing, which again shares similarities to Python lists. So if we create a list from 0 to 10, we can specify like start, stop, step. If we omit certain things, then it will be inferred as like start would be inferred as 0, stop would be inferred as like the size. Here it says size of dimension, but for 1D arrays and Python lists, it's basically, it takes us to the end of the list, and then step is inferred to be 1. So here we're omitting start and step. So this is essentially the same as saying 0, 5, 1, which gives us the first 5 elements. And then here we're omitting stop and step, which would take us to the end of the array with 1 step increments. And then 4 to 7 is like from 4 to 7, start and stop. Step is inferred as 1. And then here we're doing the entire array, but skipping every other element, because our step is 2. And then here we're doing every other element starting from the first element instead of the 0th element. Yeah, and then there's some unique ways to use this. So if you have a negative step, then it reverses it. And then if you have a negative step of more than 1, it will reverse it, but it will skip every other element. And then it starts from index 5. So that's kind of a useful thing to kind of pull out specific slices of NumPy arrays. It definitely gets more complicated when we go to multi-dimensional arrays. So x2 is a 2-dimensional array. So we're going to have to do slices from both arrays, from both dimensions, sorry. So from 0 to 2 for rows, and then from 0 to 3 for columns will give us like these first 2 rows and then the first 3 columns of each of the rows. And then each of the syntax kind of follows what we have for 1-dimensional arrays, but it's just kind of repeated for the next dimension. So this is what allows us to, this syntax is how we pull out like multi-dimensional slices of multi-dimensional arrays. So yeah, looking at this one more closely, we're going from 0 to 3 for the rows. So we're pulling like we're picking each of these 3 rows, which just happens to be all of them, and then we're pulling every other column because we're skipping every 2 steps. So we're going to pull 12, 7, 1, and then 2, 8, 7. Then you can also use that trick from earlier to reverse both the rows and the columns. So this kind of flips the NumPy array entirely. Yeah, and then we can do similar things with accesses instead of slicing. So if we want like an entire column or an entire row, we can just set this value to colon, which will just tell us like everything or every single row, but we just want like the 0th item from each column. So this gives us 12, 7, and 1. And then same thing when we reverse it, it will give us the first row of x2. And then, yeah, this is the same thing. And yeah, because we don't need the final one. Subarrays as no copy views. This is basically like saying that when we pull array slices, they're references to the existing data, which essentially means like, I guess it's easier to show. So if we print out x2 and then we assign a variable equal to like this 2 by 2 subarray, so this 12, 5, 7, and 6, which is essentially this 2 by 2 chunk of the original x2. If we modify a value within this x2 sub, this becomes 99, 5, 7, and 6. Now, if we print the original one, it will also be modified because this slice is what they call a view into the original array. So just be wary of that. Sometimes it can cause like confusion if you think you're modifying like a copy, but then it ends up modifying the original one, and then when you try to access the original one again, it's changed and not what you would expect. So to solve that, you can create a copy. There's something called a copy function, which does that. So running through these, it does a pretty similar thing. So we set it from what was previously 99 to 42. And then now when we print x2, it's still 99, even though we set it to 42 here, because we made a copy. Yeah, and then here we have reshaping arrays. So grid gives us, here we can kind of break this down a bit. I can say like, if we just delete this, we show grid, then we have a range gives us this series of numbers from 1 to 10. And then if we want to say grid.reshape to 3, 3, this will reshape our grid to a 3 by 3. So you can probably imagine that like it will shape into, like, since there's 9 total numbers, it'll shape into 1, 2, 3 in one row, 4, 5, 6 in the second row, and then 7, 9 in the third row. Yeah, so this will only work if the array matches the size of the reshaped array. So if we, let's say, like if we try to change this to 11, let's delete this, then we might run into an error. Yeah, so we can't reshape an array of size 10 into shape 3, 3. So we have to do 1 to 10. So yeah, just running through a couple examples. We're reshaping this array into a 2-dimensional array where there's 1 row and 3 columns. This is pretty similar to a 1-dimensional array, but there's just that one difference where it's a 1-row 2-dimensional array instead of a 1-dimensional array. Slight difference. We can also do a row vector, which is essentially the same thing. Column vector, which is like the reverse, and then this is the same thing with a different syntax. It's fine to just use reshape most of the time. Yeah, and then concatenation, we have, we can combine NumPy arrays into one. So an example here is we have 2 arrays defined as x and y. X is an array of 1, 2, 3. Y is an array of 3, 2, 1. And then when we concatenate them, that will combine it into one long array of 1, 2, 3, and 3, 2, 1. Basically merging these two together into one. So you can see that it looks like this 1-dimensional array. Here we can also concatenate more than 2 arrays at once. So x, y, and z will just add 99, 99, 99 to the end of it. Yeah, and then going up from one dimension to two dimensions, which is kind of the theme of what all of these like sub-chapters are doing, we can actually concatenate two-dimensional arrays as well. So if we just concatenate grid with itself, that will concatenate along the first axis. So add a bunch of rows. And then if we want to specify to use a different axis, we want to concatenate it slightly differently. And this will give us the concatenations based on more columns. So here you can see like the first one, which was based on the first axis, which is rows. We keep the number of columns the same, but it's concatenated by extending the number of rows. And then the second case, we're concatenating it along the second axis, or the first zero indexed axis, which keeps the number of rows the same, but increases the number of columns. And then here we just have VStack and HStack, which are kind of like aliases of using concatenate with different axes. This would be something more that I would recommend like playing around with than just like seeing how it works. But yeah. Finally, we have splitting arrays. So we have like this long Python. So this is a Python list. We have a long one if we want to split it into 3 different NumPy arrays. Then we can specify which indices we want to split it at. So this will split it at like the third index, so 0, 1, 2, 3. So this is the third index, so we'll split it like right here. And then the fifth index, so 4, 5. So then it'll split it right here as well. So this will give us 3 separate arrays, 2, 3, 99, 99, and then 3, 2, 1. So you can see that when we print it, this is what shows up. So here we're including like 2 splits, which gives us 3 subarrays. So that's why we're setting like 3 arrays. If we added another one, then we would have to add a 4th value. So we would have to do x4, and then this would give us a 4th split. Yeah, and then vsplit, hsplit are essentially just like aliases of split. So yeah, that was probably a lot, but hopefully that gives you like a good overview of the functions that you can use in NumPy arrays. And then once you get to kind of play with it more hands-on, I hope it will make a little more sense and feel less like I'm just rambling at all of you.
Hey, Chris, there's a question in the chat I don't actually know how to answer.
Sure, which one?
The very last one. Um, Tony D asked, what is the difference between these 2 array shapes? We want to use them. I don't know.
Yeah, so let's say Theodore answered.
Oh,
The
I didn't.
second one is 2-dimensional, while the first one is 1-dimensional.
Right.
They look very similar, but you'll eventually see that like there's, I guess, certain ways you can manipulate like 2-dimensional arrays better than you can do 1-dimensional array. For example, if we're pulling out like a specific row from a two-dimensional array, like we don't always want that to be a 1-dimensional like version, because if we're expecting like if we're expecting something to be in the format of like a 2-dimensional array, then it becomes hard to like generalize. It's hard to kind of frame given what we know so far, but I think it will start to become like more and more relevant as we work with NumPy. So just keep that in mind for now, that like they look very similar, but they're technically different. One is 2-dimensional with like one singular row, while the other is just 1-dimensional. Yeah, and it helps with like stacking, for example. So yeah, thanks for adding that. Cool. So let's take another quick break. I think this will probably be the last chapter that I would want to cover. So I'll try to I think I can hopefully finish within the next 30 minutes, but we'll see how much time I can leave at the end for questions. But yeah, another 2-minute water break, I think, and then we can get started on this. Feel free to drop questions in the chat during that break. All right. Looks like we're good on questions. So I'll start running through this final chapter, and then we'll leave the remaining time for anything people are curious about. It also helps to just, I see some people are like playing around with different like code combinations and just typing things in their Jupyter notebook. So that's definitely recommended. I think it's a really good way to just better understand, like, if I do this, then this is what happens in NumPy, and you can kind of feel out what the NumPy functions do, and kind of like how to manipulate them. So yeah, if you're doing that, would recommend continuing to do it. If not, then I would recommend trying. But yeah, final chapter is universal functions. So this is kind of getting into how we can actually start manipulating the NumPy arrays. So there's a lot of text here. Basically, the TLDR is because NumPy is storing data efficiently, we can actually modify the data within a NumPy array efficiently as well. So it's a lot faster than, like for example, finding a sum in NumPy is a lot faster than finding a sum of a Python list, because when we're finding sum of a Python list, we have to loop through it. So this next section talks about like how slow Python loops are, and how we can take advantage of the efficiency of the storage of NumPy arrays to compute things like the sum much faster, or things that require us to like loop through every element of the array much faster. So here we have, again, we're importing NumPy, and we're defining a function called compute reciprocals, which essentially just gives us like one over like the reciprocal, so one over the value of each item in the list. So to break it down a bit, we have like a list NumPy.empty. So this is like an empty NumPy array initialized to the length of values, and then we're looping through every item within values and setting this output for that index to be the reciprocal of that value. So for example, I guess here, let's comment this out. Values is equal to values. So values is equal to, for example, in this case, 61448. It's random every time. So if I run this cell again, it's gonna give me like different values. Oh, never mind. It's because the seed is specified here. Okay, that's actually perfect. So so our values are 6, 1, 4, 4, and 8. And if we want to compute the reciprocal of it, then it will give us like, 1/6, 1/1, 1/4, so on. So that's what these reciprocal values look like. So if we try to, so there's this handy function in Jupyter Notebook called %timeit. So this actually lets us see how quickly a cell of code can run, or like some like series of logic. So when we say time it compute reciprocals, this will time like how long it takes to call this compute reciprocal function, which we defined up here. And then big array is a big array of size 1 million, a bunch of numbers from 1 to 100. So if we run it, it will take, I mean, it's already like visibly taking a long time, but it will show us like it takes, so I guess it only ran one loop, and it took like almost a second to run. So that's a really long time. Let me also clear the outputs so we don't have all the old outputs. So we'll run that again, and it should show like maybe a slightly different value for how long it took to compute the reciprocals. But anyways, that's a really long time. If we're just doing something like, oh yeah, slowest run took 6 times longer than fast. So this one took like 2 seconds per loop. So yeah, anyways, yeah, ignore that. So it takes a really long time. So now we want to kind of look at how NumPy can do a little more efficiently. So hopefully we're able to eliminate like the usage of the for loop because loops are really slow. So introducing U functions, this is like the universal function from earlier. So here we like see we're calling compute reciprocals, which is the function that we earlier defined, where now we can actually just do like 1 over values. So values is like this NumPy array that we've defined here. So what you can actually see is like the result is the same for both of these, but one is using a loop and the other one is just directly dividing it. And we're able to do this because NumPy, like the storage format of NumPy arrays is what we call like vectorized. So like think of it as instead of like going through each element individually, we just do like 1 over like the entire array all at once. So it's all kind of happening simultaneously. So if we do time it of this expression, we can see that it should be a lot faster than the Python loop, although it is taking a long time right now. Let's see. This is bad for my demo, but oh, okay. So what actually happened for time it is it ran a bunch of times, and it gives us like the average. So average 3 milliseconds, and if we go back to look at the average runtime per loop for compute reciprocals, it's 1.83 seconds. So that's like a pretty significant increase in efficiency. So this will make our lives a lot better if we don't have to wait like a whole second to compute just the reciprocal of like such a big array. And imagine if we have to do something even more complicated, then it might take way longer. So vectorized operations, which is something like this, basically like in arithmetic function or operation on like a NumPy array is considered like a vectorized operation, is a lot faster than just looping through each individual item and performing that calculation on every single item in like series. So yeah, here's a couple more examples of it. We can actually do like, we can do vectorized operations between 2 arrays. So we have a range 5, which is 0 to 5. And then we have a range 1 to 6, which is I guess 1 to 6. But these NumPy arrays are the same length, so we can compute them like we can compute this division using a vectorized operation. So to better illustrate it, we can like print out both of these, or we can say like A1 equals this, A2 equals this, and then print A1 and A2. And then we can show like A1 over A2. So you can see like we have 0, 1, 2, 3, 4, and then 1, 2, 3, 4, 5. So what we're doing is like the immediate like one-to-one division of each of the individual items in the one-dimensional array. So 0 over 1, 1 over 2, 2 over 3, and so on. Yeah, and then you can also do the same thing for multi-dimensional arrays. So this is basically like saying 2 to the power of x, where x is a 3 by 3 NumPy array from 0 through 9. So we're going to say like 2 to the 0, 2 to the 1, 2 to the 2, all the way to 2 to the 8. So that shows our 3 by 3 array. And just remember that this is like a lot more efficient than if we went through each item here, especially for like a multi-dimensional array. We would have had to do something like for like I in range, what is it, x, and then like for j in range x0. So like, sorry, length. So this gives us like the number of rows, and this gives us the number of columns, and then we have to say like 2 times x, or like final, something like this, and then final I, j, something like that. And this would take a lot longer because we're doing like, and it's also just like way more complicated. So definitely much more clean to do something like this, this factorized operation. So moving forward, we have a bunch of different operations that we can do on NumPy arrays. So here's like a good example of a bunch of them. We have x is equal to range 4. So this gives us 0, 1, 2, 3. If we do x plus 5, that just adds 5 to each individual element. X minus 5 subtracts 5 from each individual element. X times 2, again, like pretty, I guess, intuitive, but it multiplies each item by 2, divides by 2, and then this is like floor division. So you can kind of see the results of each of those here. There's also like, I guess, slightly less traditional operations like negating or power or modulo that you can also do. And it essentially allows us to skip the for loop, both in like the amount of code that we have to write and like the efficiency that we can avoid like the slowness of the for loop just by directly doing it on this vector. And what's great is like, what's great about this is, or I guess what's great about NumPy arrays is that it only works on NumPy arrays. If we have like a list y that is equal to 1, 2, 3, or maybe like the same one, like we couldn't do something like y mod 2. This would give us an error because you can't do modulo on a Python list. So that's the nice thing about NumPy arrays and these universal functions. You can also combine all of these operations, and this gives us like basically this value for a bunch of different things. So yeah, this is saying here is like for every operator that we've done here, there's like a corresponding NumPy function for it. So NumPy.add is the same thing as saying like x plus 2. So these are like both equivalent. So if we did NumPy.add x2, it would be the same as saying x plus 2. It gives the same output. Yeah, there's also a bunch of built-in values or operators that we're probably familiar with in Python. So like computing absolute value, this will give us the absolute value of all the items within the list. And this corresponds to numpy.absolute or numpy.abs. So you can see that these give us the same thing. Yeah, and then here, I guess this is going back to when we were talking about a bunch of different types that NumPy supports. It can also handle complex data. So if we do an absolute value on these complex numbers, it will give us like the entire thing converted into absolute value, or I guess magnitude. Yeah, and then a bunch of these other things. I'm sure like you can start to see the pattern. Basically, like we can do all of these operations on NumPy arrays, and instead of having to compute these things individually for each item in the list, it does it for the whole list. So I'll just run through these real quick. This just gives us like sine, cosine, theta of all of these. At this point, I think it's just like it's showing off all the different things that you can do with NumPy, but like the concept stays the same. Like here we're doing log, here we're doing like exponent. We're basically able to do all of these things like in a pretty simple way syntactically, and it's like remember it's efficient because NumPy because of how NumPy arrays are stored. Yeah, and then these remaining things we can skip over. They're starting to just get like super convoluted. A lot of like statistics and like probability stuff that NumPy is like really useful for. But you kind of get the idea. You're basically able to perform all these operations on NumPy arrays.
Hey, Chris,
Um,
can I ask a couple
yeah,
questions? And so
sure.
the program knows that an object is a NumPy array because you basically defined it using like NP dot
Mhm.
array, right?
Yeah,
That's how the program knows that's a NumPy array as opposed to like a Python list or something like.
yeah,
Okay. So
yep.
do you know for these okay, so I guess is the definition of a universal function. It's just a NumPy built-in function that does a certain calculation.
Yep.
It's not anything that the user defines to be a universal function, right?
Yeah. I would guess like I'm actually not 100% sure, but I think a user can probably define their own like
Right.
universal
That
function.
was my next question. I mean, suppose, if I want to find like the median or the mode of a NumPy array and then calculate the standard deviation. I mean, there's probably a universal function built in for that, but if there isn't, can I like
Yeah.
write one? And then can you show us how to write that?
Yeah, that's a good question. So I would say like probably 90% of the time, if not more, like NumPy will already have that function existing.
Okay,
They have like all sorts of like different kinds of universal functions that you can use.
got it.
Like for the most part, like if some statistician has thought of it, it probably exists like with NumPy.
Um,
Um,
do you know if within NumPy you can like pipe functions together? Um, Kind of like within command lines, okay, you could perform like some action and then take the output of that action, which becomes like the input of another.
yeah, so you definitely can do that. It kind of just looks like, let me see. Um, I would say like, let me find a good example. Probably like one of these. Wait, is this the right? Yeah. So if you wanted to take like maybe like a double exponent or something, if you wanted to take like if you wanted to do I don't know, maybe like okay,
Well,
well, first of all, there's this, right, where you can
uh,
combine like a lot of different operations into like against one. Like here we don't have to do like let's say like we would say like a equals 0.5 times x, b equals like a plus 1, c equals negative b, and then d equals like c to the power of 2, right?
mhm,
Like this is kind of like the order of operations that's happening here, but
mhm.
we're doing it all in like one line. So if you wanted to kind of represent this in like, for example, this way, like we would say a is equal to like x np dot multiply like uh, x 0.5, right? And then if you wanted to do like plus one, then you could do np dot add,
Okay. Okay.
right? Something like this.
Gotcha. Okay.
Um, yeah.
Okay. Cool. Thanks.
Yeah, exactly. So someone, oh yeah, yeah. You would just use the function as an argument to another function. Exactly. Um, yeah. So you can do it with like all different kinds of things. I was just struggling to find example. Like I don't want to take like the power of a power or like the log of a power. But yeah, you can definitely do that. As for custom ones, I'm like, yeah, I'm not sure. Um, I would guess there is a way, but like I've never had to do it. I've never like found that I needed to do it. Um, there's NumPy has like a good series of like basic universal functions. But a lot of times in data science, like you'll use something called like SciPy as well, which is basically like just I don't know if this is like a good way to describe it, but I would call it NumPy on steroids, where it's like you can use there's like all kinds of different like statistic functions that you can put on like NumPy arrays. Um, so that might be something to like look into for those of you who are have like a background um, in statistics, but like there's a lot of cool stuff that you can do with this. Like pretty much anything that like you can think of is probably here. Um, so yeah, a lot of cool stuff. I don't know where the documentation is, but yeah, this is a lot. But yeah, that's pretty much it for NumPy. I know that's a lot, but hopefully we'll have like some more hands-on stuff that we can run through in a later session to kind of help you guys get a better feel of how to use NumPy instead of just like watching me run a bunch of different cells. Um, but yeah, practice is like definitely key. I didn't pick this up from just like watching a video. It's like definitely just, typing stuff into cells and seeing what happens. It's like the best way to do it. So I'll try to, so like, I guess we have a couple more minutes. I'll feel free to continue dropping questions in the chat. But my plan for like the remaining sessions is to cover, so like there's a couple more chapters within the data science handbook that would be, I think, useful to cover. So after NumPy is pandas, which is chapter 3. And then after chapter 3 is matplotlib, which is basically like graphing data. So I think these 3 modules in combination are like a great set of tools to have to do like a basic data science project. So I'll try to cover all 3 of these or I'm hoping to cover the like pandas and matplotlib within one session next time, and then we'll have like a big project to combine all 3 together and get a better like hands-on approach to using these things, because that's definitely the best way to learn instead of just like learning through video like what exactly each thing does. Yeah, so that's kind of what we've got planned. So yeah, feel free to continue asking questions. That's all I have for today. I'm glad we're good on time this time. There's a question: how do I get the footer on these pages? This is just part of the notebook, I believe. If you scroll all the way to the bottom, it should be there. If not, then I'm not sure. It's also at the top. Yeah, I I didn't do anything to add these, so I can't fully tell you how to get them.
I have a
Cool.
question. Vicky, can you start
Yeah, go for it.
Paul? I'd be interested in knowing how many of the participants here have installed their own IDE, VS Code or PyCharm, a third option, or nothing at all. So if that would be helpful, because I was hoping that if it's mostly VS Code, which I'm familiar with, I could kind of have a show and tell how to use it.
Yeah, this on IDE and which ones? Okay. So, okay, and so what are your choices? PyCharm,
PyCharm, VS
VS
Code, or a
Code.
third option.
Um, and then we'll have a fourth option saying have not installed.
Yeah.
Okay. I will say probably after this Friday, you will likely need an IDE. Definitely for the images, because I don't think the images would run on the SIP IDE. Okay. Some other IDE, maybe like Spider, etc. Okay. Okay. Okay, save to library, and then I'll launch this. Wait, it's being shared. A poll result is being shared. So, okay, stop sharing. Okay, and then I will launch this. Why is this? Okay, relaunch poll. I okay, end poll. Why doesn't this? Okay. Um, Hold on. Maybe I need to delete this. It's not. Okay, there we go. Okay, there we go. You guys see this hole?
Yes, I like it.
If you guys download that folder to the images file, there's actually instructions on how to download VS Code or PyCharm. If you look at the CS106A website, they they tell you to do PyCharm, but I've done PyCharm before, but personally, I think VS Code is a little bit easier to use. Okay. So I think we have like 18 people that voted. Um, Dieter, do you want me to stop it?
That's fine. I think, yeah, VS Code is by far the winner. PyCharm, two people, some other ID, three, one person not installed yet. So that person can help.